Acid-base reaction with gas formation occurs with certain salts, mostly your carbonates, your sulfites, and your sulfides. Carbonates react with acids to form carbon dioxide. Example, sodium carbonate plus HCl, strong acid, forms sodium chloride, water, and CO2. Now you might say, well, how do I know it's forming water and CO2? Well, if you do your displacement, you come up with carbonic acid, H2CO3, and anytime you form carbonic acid as one of your products, you quickly go ahead and break that up into H2O and CO2. That's a gas that will be coming off. Sulfites react with acids to form SO2, sulfur dioxide gas. Similar situation, in this case I got sodium sulfide plus HCl, forms sodium chloride and H2O and SO2 gas. Once again, same thing, if I form H2SO3, sulfurous acid, I know to break that up into water and SO2. This is when you get that SO2 gas, that's that rotten egg smell that you get. Sulfides react with acids to form H2S, hydrogen sulfide gas. Sodium sulfide plus HCl gives me sodium chloride and my hydrogen sulfide gas. Some other acid-base reactions. Non-metal oxides, also referred to as the acid oxides or the acid anhydrides, react with water to form acids. SO2 plus water gives me H2SO3. This is a combination reaction. This is what we refer to as acid rain. Metal oxides, or your basic oxides or basic anhydrides, react with water to form bases. You have Na2O, sodium oxide, plus water forms sodium hydroxide. Once again, a combination reaction. Next type we're going to talk about is oxidation-reduction reactions, or also referred to as redox reactions. An oxidation-reduction reaction involves the transfer of electrons from one species to another. Oxidation is defined as the loss of electrons. In essence, something is going to a higher oxidation state by losing electrons to something else. Reduction is defined as the gain of electrons. It's going to a lower oxidation state by gaining electrons from something else. Oxidation and reduction have to always occur simultaneously. I can't have something oxidized if something else isn't being reduced, because there's a transfer of electrons. If something's giving up electrons, something else has to be taken it on. We're saying that something is undergoing reduction. We're saying that it's gaining electrons. Or you can look at it another way. It's gaining hydrogens or loss of oxygens. It's a way to look at things to determine what's happening, what's being reduced. Look at this example. We have iron 3 going to iron 2. Okay. For this to be a balanced half reaction, a reduction, the atoms have to be balanced, one iron on both sides, but the charges have to be balanced as well. You can see that I have 3 pluses on my iron 3 and 1 negative for my electron. That's a total of 2 pluses. On the other side, I have a total of 2 plus, so that's balanced. Charges in atoms have to be balanced. In a reduction, your electrons will always be on your reactant side. It's taking on electrons. You can see in this example that iron 3 to iron 2 is going to a lower oxidation state. An oxidation is a loss of electrons or a loss of hydrogens or a gain of oxygens. In this example, we see that iron 2 is going to iron 3, and it's taken on and it's given up 1 electron. It's going to a higher oxidation state for that to happen. This is an oxidation. Let's look at this example. It's another oxidation. But when you're looking at oxidation, you need to figure out what's being oxidized in a reaction. Okay, we know this is an oxidation because it's giving up electrons too. But what element is actually being oxidized? We can go by the old standard that I know that gain of oxygen is going to be a case of oxidation. So I can see I'm going from BrO3 minus to BrO4 minus, same oxidation number of -1. So therefore boron must be changing its oxidation state. It must be getting higher for this to occur. Since I add in an oxygen, that means the Br charge has to be getting higher as well. So just by looking at that gain in oxygens, I know that Br is being oxidized. But there's another way to look at it too. We're going to look at the actual oxidation state, calculate that Br oxidation state before we can see what's changing. We must calculate the charge on Br to decide if it is oxidized or reduced in charge. We know that oxygen is -2 by the oxidation, and we know that the overall charge on the BrO3 is equal to a -1. This whole BrO3 is equal to a -1 charge. So we can set up a little arithmetic. 3 oxygens at a -2 each, that whole thing is equal to a -1. You do the arithmetic, we find that bromine is equal to a +5. Bromine is equal to a +5. Now let's look at the BrO4 minus, the perbromate ion, and see if we can calculate the charge on that bromine as well. We've got bromine plus 4 oxygens at a -2, the whole thing equal to a -1 again. Solve for it, bromine is equal to a +7. We can see that bromine is being oxidized. It's going from a charge of +5 to +7. Here's an example of reduction. 2 H pluses plus 2 electrons gives me H2. We know in a reduction that the number of electrons will always be on the reactant side while the electrons will be on the product side for an oxidation. We can see that hydrogen is going from a plus charge to its elemental state, which is a 0 charge. An oxidizing agent is a species that undergoes reduction. So, in the example we just did, H plus is an oxidizing agent. It's undergoing reduction, so it's taking electrons from something else, so it's allowing something else to be oxidized. That's why it's referred to as an oxidizing agent. A reducing agent is a species that undergoes oxidation. It's basically giving up electrons, which allowing something else to be reduced, so it's referred to as reducing agent. So bromate, BrO3 minus, is a reducing agent. Note, we need both reactions to happen. We can't have something being reduced unless something else is being oxidized. The electrons are always on the product side for the oxidation and always on the reactant side for the reduction. Copper prefers to be reduced while iron prefers to be oxidized when they're present together. Let's write the net ionic reaction for iron and copper 2 sulfate. Well, here's my molecular equation. Now what we're going to do is write total ionic equation. To do that, we need to look at our species. We know that copper sulfate is a soluble salt, so that breaks up into its ions, copper 2 plus and sulfate ions. And iron 2 sulfate is a soluble salt, and that breaks up into iron 2 plus sulfate ions, and then the copper solid comes down. Now to write my net, I have to get rid of my spectators, and the only spectator we have is sulfate, so if I get rid of that, I get my net ionic equation. I have iron solid, which is its elemental state, 0, plus copper 2 plus, giving me iron 2 plus its copper elemental state, which is a 0 charge. You can see in this example, in my net ionic equation, that it's going from a 0 iron to a 2 plus, and a 2 plus to a 0 copper. We have iron being oxidized and copper being reduced. In this oxidation reduction, iron 0 has lost 2 electrons and was oxidized to iron 2, while copper 2 gained 2 electrons and reduced to copper 0. So we went from iron 0 to iron 2 plus, which was a decrease by 2 electrons in the oxidation process. The charge is basically an inventory of electrons as compared to protons. So a positive number means the neutral species lost electrons, while a negative number means the neutral species gained electrons. Copper 2 went to copper 0, and that's a case where it increased by 2 electrons, so its oxidation number went lower, and it's a reduction. Iron solid is a reducing agent, since it's undergoing oxidation, and copper 2 plus is an oxidizing agent, since it's undergoing reduction. Notice that in this net ionic equation, the atoms are balanced. They have one iron on both sides and one copper on both sides, but the charges are balanced as well. On the reactant side, you have a 0 for the iron and 0 for the copper. So you have 0 for the iron and 2 plus for the copper. That's a total of a plus 2 on my reactant side. On the products, you have 2 plus and 0 for the copper solid, giving you a 2 plus. So it's balanced, charges as well as atoms. Which gets us to the topic of oxidation numbers. How do you know the numbers? How did I know that iron was a 0 and copper was a 0? The concept of oxidation numbers is a simple way of keeping track of electrons in a reaction. The oxidation number, or oxidation state, of an atom in a substance is the actual charge of the atom if it exists as a monatomic ion. Alternately, it's a hypothetical charge assigned to the atom in the substance by some simple rules. A lot of them you're already familiar with. Here is your oxidation number rules. Elements. The oxidation number of an atom in an element is 0. Those species in the elemental states have a 0 charge. So you're looking at iron solid, that's a 0. H2 gas, that's its elemental state of oxygen, it's a 0. Bromine liquid, Br2, it's a 0. The elemental states at room temperature have a 0 charge. Monatomic ions, the oxidation number of an atom in a monatomic ion equals the charge of the ion. That goes back to the periodic table when we said group 1's a +1, group 2's a +2, etc. Oxygen. The oxidation number of oxygen is 2- in most compounds. The exception being in the peroxides, say oxygen and H2O2. Basically you're looking at O2 with a 2-, so each oxygen is really a -1 charge in the peroxide. Hydrogen. The oxidation number of hydrogen is +1 in most compounds. The exception would be the metal hydrides, because the metals are going to be the cation and the hydrogen will be the anion in that case. So hydrogen tends to be a -1 when it's the metal hydride. The halogens. Fluorine is -1 in all compounds. The other halogens are -1 unless the other element is another halogen or oxygen. That gets you into your oxyanions. Your compounds and ions. The sum of the oxidation numbers of the atoms in a compound is 0, as we've been doing all along, and the sum in the polyatomic ion is equal to the charge on that ion. So let's calculate some oxidation numbers. Let's look at sodium sulfate. We know by the rules that sodium is a +1 because of the monatomic charge, group 1, and we know the oxygen is a -2 since it's not part of a peroxide. But how do we figure out that sulfur? You can determine charges based on the whole compound being equal to 0. So we can say sodium sulfate is all equal to 0 and solve for that sulfur one. And using the rules to determine the charges with calculating the unknown charges. So we know sodium's +1. I have 2 of them. I'm trying to find sulfur. We have oxygen, which is -2, and I have 4 of them. And the whole thing is equal to 0. This is a neutral compound, so we know that whole thing is equal to 0. Solve for my sulfur doing some arithmetic, and we find out that sulfur is a +6. Now, we could also just do it based on the ion. We know that sulfate, SO4, is equal to a 2- charge. So we can just do it based on that. And we have sulfur, we have oxygen a -2, you got 4 of them, the whole thing is equal to a -2. Solve for sulfur, which would be +6. Same result. Let's look at these 4 species and see if we can come up with the charge of chlorine. Well, Cl2, if we're talking about room temperature, that is its elemental state, so that's a 0 charge. If we're looking at ClO2, there's no charge to that. I have 2 oxygens. That's a minus 2 times 2. That's minus 4. Therefore, chlorine has to be a 4 plus for that to be neutral. ClO2 minus. Well, I have 2 oxygen again. That's minus 4. But the whole thing is equal to a minus 1. So therefore, this chlorine has to be 3 plus. And then we have Cl2O5. It's a neutral species. I got 5 oxygens and minus 2. That's a minus 10. And I have 2 chlorines. The whole thing's equal to 0. Therefore, this chlorine has to be plus 5. So 0 for Cl2, plus 4 for ClO2, plus 3 for ClO2 minus, and plus 5 for Cl2O5. Homework 31.